Hello, Rejuve, and everyone watching. Welcome back to another episode of Healthspan Horizons. And this is episode 8. And I'm Jasmine, CEO of Rejuve.AI. And we got Melissa, Director of Marketing. And today we have kind of a special episode, special guest, if I may say, one of the OGs of longevity, um, Dr. Aubrey de Grey, who, kind of needs no introduction. But, there may be some people out there who are not as familiar in longevity space. So maybe you can give just a brief introduction to what you have accomplished in the past, 20 odd years or so.
Yeah, thank you, Jasmine. Thank you for having me. So yes, it's quite amusing to me actually to be described as one of the original gangsters because of course, everybody who has contributed to any particular crusade or field builds on the shoulders of giants that came before. And I certainly did that. And one of the giants in question was also the person who originated the work that you do for your day job, Michael Rose, who in the 1980s, of course, started an experiment that is still going on that extends the lifespan of fruit flies. And not only was that extremely successful in terms of its scientific value and generally made his name and caused him to be, I think, the youngest ever full professor in the University of California system, but also he made a lot of use of that prestige of becoming that way by making clear to anyone who was willing to listen that aging was quite a bad thing and that we should really try and do something about it, which was still a pretty dangerous thing to say 20 years later when I started saying it. But yeah, it was particularly dangerous when he started saying it. I think he basically got away with it because he was only an evolutionary biologist. I use the word only in scare quotes, of course, because yeah, um, because if you were an experimental biologist in most ways, then you definitely couldn't say things like that back then. But thank you. Yeah, so I got into this field kind of by accident because I didn't actually start out as a biologist at all. I started out as a computer scientist, and around the time that Michael was starting to do his thing, I was just embarking on a career in artificial intelligence research. I started out doing my undergrad degree in computer science at Cambridge, and then I worked on a field called software verification, which basically means writing programs that find mistakes in other programs, um, which was a big topic in artificial intelligence research back then. Artificial intelligence was very, very different in those days than what it is now. Back then, it was generally believed that neural networks, computer programs that essentially emulated the structure of the brain, were completely incapable of doing hard things. And that the only way you would ever actually develop real artificial intelligence was symbolically. In other words, by writing programs that would um, prove theorems and so on. And that's the kind of work that I did. So I'm very much not an expert or even a novice at the kind of AI that exists today. Um, but then, so that was all very well. But while I was, being a perfectly self-respecting computer science researcher in the mid 1980s, actually in the early 1990s, I met and married a biologist who was a lot older than me, already a full professor at UC San Diego, actually, um, was in England on sabbatical. And through her, I learned a lot of biology over the dinner table by accident. But I also, eventually, after a couple of years, began to realize that she wasn't interested in aging. And actually, that none of the other biologists I was meeting through her were interested in aging either. And I thought, well, what? How come? Because I'd gone through my life until then under the false assumption that absolutely everybody thought that aging was the world's, most important, most major problem. Causes the most suffering, causes the most death. It was completely obvious to me, and it had never really occurred to me at all that other people might not think that way. So once I found that out, I thought, well, that won't do. And by this time, I'd done quite well in my AI research. I had come to the conclusion that I was pretty good at working on hard problems. So I thought, well, I've got to switch fields, really, and here I am.
Amazing, and of course that's very synergistic too with the AI field. Yeah, of course, Rejuve is a spinoff of SingularityNet. Dr. Ben Goertzel, and he's still working on that neurosymbolic AI. Is actually a big proponent of that. So interesting that you mentioned that. So yeah, I guess so. You talked a lot about kind of the field and how you came into it. So tell us about your current endeavor, the Lev Foundation. What is it all about? What's the goals and mission, vision, and what's like your aim for it?
Yeah. Well, bridging to that, when I started in the field, when I switched fields, of course, spent a few years just learning and listening and meeting people and so on. And then I had a fairly important kind of eureka moment in the year 2000, which is basically to realize that the most practical way of actually achieving what I wanted to achieve, namely the medical control of aging, would not be by slowing aging down, but rather by reversing aging, by actually repairing the damage that the body inflicts upon itself throughout life that eventually makes us sick. Um, and since that time, I've essentially split my career into two parts. One part is community building and advocacy and so on, because around about 2005 or so, I started to get quite a bit of attention from the mainstream media and, get lots of conference invitations and so on. And I have made use of that to draw people into the field and to essentially get more people to help me do what I want to do, namely to bring aging under medical control. And the conferences that I run, one of which, of course, you just attended, Jasmine, in Dublin a couple of weeks ago, are a huge part of that. They are enormously effective in bringing people into the field, getting people to meet each other, and so on. But in parallel with all this community building, I do, of course, also oversee and pursue research into developing these interventions. I focus on the early stage research, the stuff that is so early that most people feel it doesn't fit with their incentives. So it's not short term enough. It doesn't make money quickly. It doesn't get you a lot of papers in Science and Nature and Cell and your next grant application funded and so on. So I chose to work on things that I felt were just as important as the ones that do get those things, but that were being neglected. And the way I chose to go about it was to create organizations that were supported entirely by philanthropy. And with philanthropy, of course, there's no us covering, right? You don't have to be answerable to your shareholders. You also don't have to be answerable to the people who are going to decide whether to give you your next tranche of money from the government. Um, and that means that you have a lot of freedom. You only have to persuade the people that you're having a beer with, who might be in a position to write large checks. So that's what I did. And Lev Foundation, as you say, is my current organization. It's the third one that I have run, but all three of them have been 501c3s, which, of course, is the American term for a public charity. And and they have been doing research, biomedical research in cell culture or in mice, not in humans. As I say, I work on the early stage stuff. So, Lev Foundation is focusing on the most important and indeed most neglected aspect of any of the divide and conquer strategy that I have been pursuing over these years. This is the nature of damage repair. When I realized 24 years ago that we should be repairing damage rather than trying to slow down the rate at which the body creates that damage in the body, damage at the molecular and cellular level, I immediately acknowledged that this meant that we had to develop a bunch of different interventions that would address different types of damage. And we would have to, give people all of these things at the same time, which, of course, is very antithetical to the way that medicine is normally done. Medics try to keep things simple. They try to understand whether they're going to have unintended consequences of what they do. Very reasonable. But the fact is, we have to bite that bullet in the case of aging, because aging is a really, 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 really complicated phenomenon. And, you can take end runs around that complexity if you're working in the lab. And of course, Michael Rose took a spectacular end run by leveraging the power of evolution, but evolution only works in small increments from one generation to the next. And I'm quite interested in people who are already alive, such as Michael or myself, for whom evolution is not an option. So I have to take a different strategy. And as I say, the strategy is very much a divide and conquer strategy. So that means you've got to develop the individual components of the strategy, and you've also got to put them together. And so LEV Foundation is focused on putting them together, on taking things that already have modest benefits in mice, in terms of being able to extend the longevity of mice, even if you only start giving them the intervention in middle age. So middle age for mice means about a year and a half old, because they normally live to about 2.5. And so that's what we're doing. We've taken 4 of the most justified interventions, things that a number of people have published on in the past, showing a modest increase in lifespan and health span. And we're doing them all at the same time, and it seems to be working fairly well. I could go into details, but of course, I actually have one of the luxuries of leading a nonprofit, which is funded entirely by philanthropy, is I can be public all the time about the results. So I do that. I put updates out every month on social media. People who work for me are not looking for their next job the way most people who work for a professor at a university are. And that's very liberating for me. But yes, anyway, the long and short of it is that in the female mice, it's rather boring that essentially all the impact, all the benefits that are being obtained by one of the 4 interventions, namely rapamycin. But in the male mice, that's not the case. In the male mice, we are very much seeing additivity, which is what we were hoping for.
Well, I actually have some questions about the mice coming up later. So we're gonna circle back to that because
Great.
it's very interesting. But my next question following this is I'd love to hear a little bit about your longevity escape velocity. First, if you want to explain in layman's terms what that is, and then whether or not you how we're gonna know if we've reached it. I think that this is kind of a hot topic in longevity because some people already claim to have reduced their biological age and stuff. So is this different? Is it better? Is it the same thing? What are your thoughts?
Yeah, okay, yeah. Thank you for asking. There are a few important points to raise and things to explain there. So, first of all, what is longevity escape velocity? This is a term that I defined 20 years ago. And it has taken a long time to become mainstream, I will say that. When I started out, of course, the whole idea of bringing aging under any kind of medical control was not very mainstream, to say the least. In fact, the only way in which it was mainstream was kind of a false dawn. So I mentioned at the beginning that Michael Rose was one of the real original gangsters 20 years before me. If I had to name anyone who came between him and me, there's only really one candidate, and that is Cynthia Kenyon, who figured out in 1993 that by mutating just one gene in nematode worms, which live even less time normally than fruit flies do, you could double their lifespan. And that has proven to be a very robust result. In fact, people can now multiply the lifespan by 5 or 10 times. But these worms only live 3 weeks in the first place, so whether that's exciting or not depends on your point of view. But what's rather more demoralizing about this approach is that even in the 1990s, people should have realized that it wasn't going to work for humans. Because the gene in question, and indeed other genes that were found that did more or less the same thing, are part of a pathway that nematode worms use to respond to famine, to not having enough food. And that is a phenomenon that was observed in mammals, specifically in mice and rats, a century ago, in the 1930s. It was found that if you feed mice or rats less than what they want, then they'll live longer than normal. But they don't live 5 or 10 times longer, or even 2 times longer. They only live about 1.5 times longer at maximum. So you may think, well, that's still quite a lot, but everyone kind of swept under the carpet the question of why you can't do the same thing that you can do with nematodes. They said, well, okay, nematodes are a bit special. They
They're just
are,
tiny. I
they
don't
have
know.
this thing called the Dower pathway, where they essentially become a spore. This kind of spore, and they don't have any food at all, and they just hunker down until food comes back, and they have chemosensory ways to detect when to wake up. But that's actually a bit of a cop-out to say that, well, the Dower pathway makes nematode worms not really comparable. Because you can do it with other organisms. In fact, if we talk about fruit flies for a moment, fruit flies have something called diapause. Fruit flies live only, maybe 6 or 8 weeks on average. You might be able to get them out to like 10 or 11 weeks if you treat them really well. Robin Mockett, another British researcher, of course, Michael Rose is not British, he's originally Canadian, but he started this famous work in Britain during his PhD. So Robin typically gets his flies to live maybe 70 or 80 days. And this is without any evolutionary selection. So that's the kind of gold standard. But the thing is, you can get them to live a lot longer than that. People don't ask the question, how do flies get through the winter? I mean, what the fuck, right? The winter is longer than 70 or 80 days. And yet they
Yeah.
do, and the answer is this thing called diapause, which is kind of like the Dower pathway in nematode worms, but without the morphological changes. They just stay looking like fruit flies. It's not just the temperature. This was discovered a long time ago that some flies, they go into diapause when it's cold, but other fruit flies, other species, there are other triggers. So again, it's because of lack of nutrients, because of lack of food. And again, coming back to the fact that we're talking about Michael Rose, let me explain this from an evolutionary context. Evolution cares about the passing on of genetic information. And that means it doesn't care about old individuals, because old individuals have already had their offspring. And this is the fundamental reason why we have aging at all. We have aging because there are types of damage that the body does to itself that accumulate really, really, really slowly, such that they only become pathogenic in old age, when you have typically passed on your genetic information. And that's why evolution hasn't taken the trouble to develop ways to eliminate that damage the way it has for types of damage that are generated at a more rapid rate and thus would otherwise kill you before you had reproduced. So in the case of famine, you have the same kind of thing. Famine happens every so often, and if if you reproduce during a famine, you're wasting energy because the fact is your offspring are not going to live long enough to have their own offspring because they're going to die of starvation. So you don't do that. You change your metabolic priorities to hunker down, and rather than putting energy into reproduction, you put energy into maintenance and staying alive long enough to outlive the famine and to get to a point where your offspring are going to continue to have their own offspring and so on. This is the technical term is bleeding obvious. But the fact is, it was swept under the carpet for a hell of a long time. But it was known. As I mentioned, nearly a century ago, back in the 1930s, people discovered that you could make mice and rats live longer than they normally would by simulating famine, by not giving them much food, but not so little food that they would starve to death. But you'd only get them to live 1.5 times longer than normal, not 5 times or whatever. And sure enough, when people tried it with longer lived species, the effect was even weaker still. People tried, Purina actually ran an experiment on calorie restriction in Labradors, which live normally 11 years or so on average, and they got like 10% increase in life extension. The NIH and the University of Wisconsin in Madison both ran experiments starting again back in the 1980s on calorie restriction in primates, in monkeys. And sure enough, they got a few percent. Actually, one of the experiments didn't even get that, but that was a kind of mistake. Well, actually, they were both actually done in ways that you might have redesigned in hindsight. But long and short of it is, there's this very clear inverse correlation. And it all arises from evolution. It's simply because long famines don't happen so often as short famines. And therefore, the evolutionary selective pressure to have the genetic wherewithal to respond to famines, again, varies depending on how long the famines are, because it varies depending on how frequent the famines are. Short famines that last, a year happen often enough that evolution takes the trouble to develop machinery to respond. Famines that last 10 years do not happen often enough for that. And therefore, lo and behold, here we are, pretty much however long your natural lifespan is, the life extension that you will get is not proportionate to that at all. It is roughly absolute. It's roughly a year, whatever your natural lifespan, whether it's 3 weeks, whether it's 2.5 years, whether it's 100 years. So that's a bit of a shame. And the reason I went into all that extensive digression was not just because I'm talking to someone who works for Michael Road or works on the work that was
yeah.
done this, but also because Cynthia Kenyon essentially leveraged all of this, and that's a bit of a shame in a way because it was a false dawn. Since it's not going to actually deliver a significant life extension for long-lived species like you and me, it should not have become the central focus of the field. But I don't want to diss Cynthia Kenyon at all here, because the fact is 2 other things were very important. One thing was that despite being a false dawn in terms of the actual specifics, it made gerontology respectable. It became a thing that you could actually test hypotheses in the biology of aging, which you hadn't been able to do before that. In the days back when I was, discovering that my wife didn't care about aging, she told me, yes, there are a few biologists who work on aging. And I said, okay, go on. And she said, well, Francis, it's descriptive. Now, descriptive sounds like a compliment, but it isn't. It's a euphemism for it's a haven of mediocrity. It basically means you can't test hypotheses. So what the fuck? Why bother? Right? And that people basically go into gerontology because they can't cut it in other more legitimate areas of biology. This was genuinely the view that not only my wife, but biologists in general had back then. And indeed, it was somewhat true. When I got into the field, I did discover that there were a lot of fairly mediocre people in the field, and not very many smart people. There were some smart people, some very smart people, but not very many. Um, and so, Cynthia changed all that. Cynthia made it possible to test hypotheses because you could make, mutants, mutant flies, mutant worms, mutant mice, and the result was you ended up being able to test hypotheses in a way that was, that felt familiar. And the result was lots of very smart, bright, young professors came into the field around that time. And that changed the field enormously. The field became respectable academically. It still wasn't respectable biomedically. Talking about actually doing anything about aging was still something that you could not mention in a grant application at all if you actually wanted it to be funded. But that did happen. And you're going to have to remind me what my question was. Your question was that you asked me like 5 or 10 minutes ago. Did I have gone on a bit of a stream of consciousness there, as you can probably
I was asking about your longevity escape velocity and your thoughts in
Yes.
comparison
All
to
right.
decreasing biological age, etc.
Thank you. Yeah, thank you. So the reason I went into all of that was because we will not get significant life extension more than a few years by emulating calorie restriction. That is not to say that drugs like rapamycin, which are calorie restriction mimetics, drugs that trick the body into thinking it's in a famine when it isn't, are in any sense valueless. They're certainly valuable because they, every little bit of extension of healthy lifespan is better than nothing, but they're definitely not the fountain of youth. And I knew this back in the late 90s. It was pretty obvious to me that there was only so far we could get in that way. And that's where I came up with the idea of damage repair, of actually reversing aging, and the realization that reversing aging was going to be easier than slowing aging down. So what does that mean? Well, what it means is that we can help people who are already getting on, who already have the misfortune to be alive. We can't do that. We can't genetically modify, people who are already alive, at least not very well, not yet. But we can, do other things. And I care about people who are already alive, you know. So I thought, well, okay, this is quite important that we can actually rejuvenate people because it means you can take people who are not just alive; they're not just like kids; they're in the middle, in like their 60s or whatever. You can take somebody in principle who's in their 60s, and you can, make them biologically 40 again. That would be quite handy, really. And there's two ways in which it would be handy. First of all, it's a bigger effect size than what you would get in the case of calorie restriction or calorie restriction mimetic. But also, and here's the really critical thing, you buy yourself time. I don't mean that you buy time for the person who is benefiting, who is receiving the therapies. I mean, it buys the scientists time. Think about what's going on here. You've got your person who's 60 years old, and they are, receiving these rejuvenation therapies. And I'm saying, hypothetically, you might be able to take them back to being biologically 40. Now, why not biologically 20? Answer is that, as I mentioned maybe 20 minutes ago, damage repair is a divide and conquer strategy. It's something where you need to fix a lot of different things at the same time in the same people. And of course, some of those fixes are easier to develop and implement than others, right? So the first generation rejuvenation portfolio is going to be incomplete. It's going to do some repair and not other repair. So let's say, let's define our terms here. Let's just say, okay, the damage that it repairs, this first generation rejuvenation portfolio, is called the easy damage and the rest is called the difficult damage. Then you've got some of each, and that's why you get some rejuvenation back to, let's say, biologically 40. So now what's going to happen to our hero who's getting these therapies? They're going to, they're going to carry on aging. It doesn't matter how often they get the therapies, is the key point. The therapies are still only going to fix the easy damage, not the difficult damage. and the difficult damage is still accumulating. So eventually, let's say by the time the person is 80 and they're going to be biologically 60 again, because all the difficult damage has been continuing to accumulate. And even however little easy damage they have, because they're having these therapies all the time, they're still going to have as much difficult damage as what they had in terms of the difficult plus easy damage when they were actually chronologically 60. So they're kind of biologically 60 again in the sense of the total amount of damage they have, and thus the the pathogenicity, the likelihood that they're going to get sick. But it's not really the same because all the damage they've got is difficult. And if that were the end of my story, then the people would just carry on getting old and dying, and that would be not good, right? It would be good in the sense that they'd have 20 additional years of healthy life before they get sick and dead, but not good enough. And so, the key point here, the key loophole in that rather pessimistic logic, is that we've had those 20 years, during which people like me and you will have been beavering away, improving the rejuvenation portfolio. And we will have had some success in that period. In figuring out how to fix some of the difficult damage. Not all, but some of it. Essentially shifting some of the difficult damage into the easy category. So when our hero comes in at age 80, having become biologically 60 for the second time, we are going to be able to rejuvenate them and make sure that they won't be biologically 60 for the third time until they're chronologically, let's say, 100 or 110, right? By which time, you got the story, right? You know the next stage. We're going to have continued to move more things from the difficult side of the fence into the easy side, and we're going to be able to rejuvenate them again. So what does this all add up to? It adds up to a concept that, as you say, I called longevity escape velocity. The idea that there's a minimum rate at which scientists have to improve the comprehensiveness of the therapies in order that people who are benefiting from the state-of-the-art therapy at any given time are going to stay one step ahead of the problem and are never going to have enough damage in their body of any kind to make them sick. And, this is such an obvious concept, and it really, really astonished me 20 years ago that it was so difficult for people to take on board. I had a bunch of difficulty getting people to take on board the idea that damage repair could be easier than slowing down the creation of damage in the body. But I expected that because that was a huge paradigm shift for the field. And sure enough, it took me several years to really get that across, to get people to understand that I wasn't talking complete gibberish. But I did succeed. And eventually that success was manifested as a paper called The Hallmarks of Aging. So that took time. The thing that really, the coup de grace that really ended the whole controversy about damage repair was a paper called The Hallmarks of Aging that came out in 2013, and which was essentially a root and branch restatement, albeit not a particularly perfect one, of what I had said a decade earlier. But unlike what I said, The Hallmarks of Aging was published in Self, and it was authored by a bunch of very influential people, and, its time had come, shall we say. So it has, of course, become by far the most highly cited paper in the entire field of the biology of aging this century, and I'm quite sure it will stay that way. But the result is very gratifying, even though they didn't give me any credit. Nevertheless, the fact is, I do not since the day that paper came out, I have not needed to justify my, my concept of damage repair. So that's wonderful. That's wonderful. But what's not so wonderful is that the concept of longevity escape velocity has yet to achieve that same degree of legitimacy within the academic field. And that's shocking because it's just maths. I mean, Jesus. In fact, the people who have been most ready to say publicly that yes, longevity escape velocity is a thing, are the people who did their undergrad degrees in maths. So Brian Kennedy and Steve Horvath, people like that. It just tells me biologists are really not very good at
Yeah.
maths. But anyway, here we are. So that's of course, the fights that I've had with Michael Rose over the years, coming back to him because I like to do that, basically because he thinks he's the only person in biology who's any good at maths, and he's wrong. And when he makes mathematical mistakes, it's hard to persuade him that he has. But there you go. I won't go into that anymore.
Well, I will say that getting into the more scientific side of longevity, this idea of longevity escape velocity stood out to me probably more than anything else. But I guess I just always kind of thought, how can you? It's kind of like the concept of singularity, right? Like one can argue that we're already there because we're at a point where technology is advancing so rapidly that it's altered our entire existence. And I think that, okay, maybe somebody's already reversed, someone like Brian Johnson's already reversed their biological age enough to where they will, live long enough to contribute to that next wave of technology that will, continue that trajectory. So I guess that's the.
I will say I am a bit skeptical about that. I believe that true achievement of longevity escape velocity uh, requires us to postpone aging initially with the first step by at least 20 years. And I don't think anything that we have today can do that. A lot of people like to say that they've done that by various measures of biological age, but I think that they only say that because they're using the wrong measures. And that actually we're going to need to do quite comprehensive stuff with gene therapies and cell therapies that don't yet exist in order to genuinely get anybody to longevity escape velocity.
And like, what kind of measurements will that be to really prove, yes, we reversed everything versus, these tests that are out now? There's lots of biological age tests and different biomarkers and all this kind of thing.
Right. At the moment, I think that the more fashionable omic-based measures of biological age are not really ready for prime time. That they are too unreliable. They're too there are too many different ones that give different answers for the same person at the same time. We're going to have to do better. Therefore, at the moment, the ways in which I think biological age can be measured are still the traditional ones, functional ones, things like, memory and grip strength and gait speed and the low tech ones, so to speak. And I get that done on myself regularly, and I am pleased to say that I always do very, very well. But fact is, I do not have any reason to believe that the things around today that can do even better, even for people whose biological age is greater than their chronological age. There are some things. I mean, certainly the biologically older you are for your chronological age, the easier it is to do something about it. A lot of people are biologically old because of type 2 diabetes, for example, which is so easy to deal with just from, being really regimented about your lifestyle, that there's a question as to whether it should really be called a part of aging at all. It's much easier. We can actually do something about type 2 diabetes. But yeah, so as I say, I don't think we're at longevity escape velocity yet for anybody.
Okay, enough. I have two follow-up questions with that. So my first one, since you said you're measuring your gait and everything, has your biological age decreased since you've been tracking and things like that? And then my second question was, okay, well, when do you think that we will actually achieve that? There are some people that, have very specific years of when we're going to get to that point where we're living forever, death is an option, things like that. So I'd love to hear your thoughts on both of those.
So for me, when I started having these measurements on myself, which kind of happened by accident as a substitute for an honorarium for a talk back in 2002, I was already doing really, really, really well. So no, I have not implemented any changes to my life in the meantime that have made me move from being average for my age to being better than average. I was already much better than average. And of course, what that actually has resulted in is the opposite of changing things. I have chosen to be quite conservative and to just keep living the way I normally live, because, if it ain't broke, don't fix it kind of thing, right? This is not to say that I recommend that other people should carry on doing what they do. It's because of the fact that I seem to be well built, and just to be naturally aging slowly. Um, in terms of when, so of course, most of my colleagues in the field will run away very fast when you ask them a question like that. They absolutely refuse to give time frames because they don't want to overpromise and underdeliver. Or, let me say it more accurately, they don't want to be accused of overpromising and underdelivering by the people who sit on their next study section. Because, everybody who evaluates whether to give money to this person or that person wants to cover their ass because they know they're going to have to say no to nearly all the applicants. And they view some excuses for not funding somebody as more us covering than others. And one of the most splendidly us covering ones is, oh, this guy keeps saying irresponsible things in public. So people don't do that. But yeah, so I don't have that problem because I get my money from people that I actually have a beer with rather than people that are hired by the government. And so I feel I have a responsibility to give a straight answer to that straight question, which of course is on everybody's mind. But there's a difference between a straight answer and a definitive answer. So my answer is probabilistic. I say that we have a 50-50 chance of delivering longevity escape velocity within the next 12 to 15 years. So the second half of the 2030s. But only a 50-50 chance because we just don't know what obstacles we're going to encounter. Any pioneering technology is like this. So I think that there's at least a 10% chance that we won't get there for 100 years, which would be a shame, but who cares? The fact is a 50% chance is quite enough to be worth fighting for.
Yeah, so actually the whole the concept of what you said, if it ain't broke, don't fix it, that's like actually, yeah, one of my mottos. That kind of goes into another thing that I just kind of observed in the context of centenarians and super centenarians, people that have already lived past 100. When they kind of reflect upon how it is that they got there, a lot of times they were not trying. They weren't extreme biohackers. They weren't, intentionally even thinking much about it. They were just simply living their lives and doing what they do. And sometimes they even do things that are kind of known as unhealthy. Sometimes they say, oh, yeah, I smoke a cigarette and have a whiskey every day. And they've been doing that every single day. So is there some kind of biological or scientific grounding for that aspect of just a homeostatic sort of not varying too much of anything, even if it's something that's not recommended?
Yeah, there is a phrase that says everything in moderation, including moderation. But no, it's not really that. So you're quite right. People have been studying centenarians for a long time, and they've been trying to figure out how they got that way. So as to give hints to what we might be able to do medically, or indeed in terms of lifestyle or diet or whatever, to help other people get that way. It's been futile. It's been absolutely the most soul destroying, frustrating field. There's basically nothing that they have in common. And, people have tried, obviously, to identify genetic things. There's a one gene, ApoE, which is an exception. As is well known, there are 3 variants of ApoE in the population. One variant is particularly bad for you in terms of the age of onset of both atherosclerosis and Alzheimer's disease. But that's basically it. There are other things that have been found more recently, took a long time to be found, precisely because the contribution that they make to longevity is minuscule. So is there any hope in learning anything from centenarians? Well, maybe. The first thing is that they do have one thing that is kind of in common, which is that nothing bothers them. They have not necessarily lived particularly stress-free lives, but when they encounter a stressful situation, they just roll with it really well. Unfortunately, even there, it's a little bit difficult to know whether we are just, victims of ascertainment bias, because, we didn't interview those same people 50 years earlier. We only interviewed them when they already had the luxury of being the matriarch or the patriarch of their family and their surroundings, and generally, having plenty of time to form a high opinion of themselves. So that may again be self-fulfilling. But we do know that there's some genetic components, some heritability to longevity, not just across species, but within the human race, in the sense that the offspring of centenarians live a little longer. Let me give you a tidbit. So I am also pretty interested not only in centenarians, but in super centenarians, people who live more than 110. Of course, there are very, very few of those people. Literally 0.1% of people who get to 100 get to 110. And that could be handy. It could be that, there's more of a, let's call it a signal to noise ratio. You can actually, you can, if you take 10 dice, then you can get, a total of 58 by rolling 10 dice in a lot of different ways. But you can only get 60 by rolling them in exactly one way. They've all got to be sixes. So it might be that, the super centenarians have really rolled some serious dice. And a few years ago, I did some innovative mathematical analysis on the ages of death of supercentenarians, which turns out to be something you can't do for centenarians or anyone less than that, simply because it's hard to get hold of the data on exactly how old they were when they died, as in to the day. Whereas with supercentenarians, there's a community of enthusiasts who actually document exactly that thing. You go to the day. And it turns out I was able to figure out a new way of analyzing data that relies on that. You can't do it unless you have it accurate to the day. But you can get more information out of it. And, well, short story is, I found that the distribution of ages at death of supercentenarians, especially of people who get over 114, which is very few people, cannot be explained easily, and can probably only be explained by the existence of genetic variation at a very small number of loci, possibly only one locus, possibly only one gene. Because when you have that, Mendelian inheritance looks different at a demographic level. You basically have a bimodal distribution of the consequences. And, well, anyway, that was a tidbit because I'm in the process of writing that up in collaboration with another mathematician. And so you'll see more of that in due course.
I think this is like one of the takeaways that we take from every podcast is essentially that when we talk about centenarians and super centenarians, there's always just, everyone's just like, yeah, they don't care. They've lived through the Great Depression. They've lived through world wars. They've lived through all this stuff. And they just keep going with it. And I think it speaks a lot to the impact that other items like mental health and resiliency and stuff to come into play in terms of longevity as well. But we don't have a whole ton of time to dive into such things, unfortunately. Otherwise, I would, because I think that
yeah, I talked to you.
That's okay. We only got a couple more questions because we're gonna have to wrap it up because no one's gonna listen to something that's 2 hours long as much as we would love to.
Some do, but
some do, yeah. All right, Jasmine, take her away. We got I think 2 questions left. So
well, there would be more, but I guess maybe we can go to maybe a couple interesting things, or I'll try to merge it a bit to get some perspectives. I mean, one of them was about a new kind of longevity therapy that I was kind of reading about, or potential one that has to do with something called bioelectrome, where they're kind of testing out making druggable targets out of the electrical kind of currents that our body and action potentials and things of that nature, and maybe being able to grow organs and all that. What do you think of that?
So I'm going to give a fairly short answer to this, not because I am unimpressed by the work, but because I don't really know much yet, or more to the point, because nobody knows much yet. So this has been pioneered by a professor at Tufts named Michael Levin, and it's absolutely fascinating. It's so fascinating that I had him speak at my conference back in 2023. He was a real hit. Yeah, extraordinary work that he's doing. But I really need to emphasize that as of now, the impact, the benefits that he's able to achieve by manipulating the electrical environment of cells are only being seen in amphibians, which have, obviously, in some cases, very much greater regenerative capacity naturally than what we do. Of course, the goal is to make it work in mammals, and he's doing his best, but, there hasn't been much progress yet. So while it's an absolutely fascinating area, I do not want to, get ahead of that. I don't want to try to say that it's going to be the way we get to longevity.
Yeah, it's definitely interesting. And then I guess maybe this can be a quick one before we finish off with a little bit of crypto and Web3 because, we're in that industry. Since we have so much data about mice, right? Like it's probably been like that's the animal that has been associated with doing lab experiments forever. And I saw at your conference, there's this thing called Open Worm, where it's like an AI simulation of the nematode worm. Do you think that we will soon get to that point where we can fully simulate the mouse and kind of be able to validate that with the real one and like prove that it's exactly the same or anything of that nature?
That depends. So, as you say, people are now at the point where they feel they can get really interesting information by applying AI to data that we've already got in nematodes. And perhaps even in fruit flies, but nematodes are even better by virtue of being self-fertilizing hermaphrodites. They are very much easier than your typical organism to do genetic experiments on. And long and short of it is, we know an awful lot about nematode worms. And so, that's where AI starts from. AI is not some miracle that generates knowledge out of nothing. It starts from a body of existing knowledge. In fact, the reason why AI is where it is today is because one guy named Geoffrey Hinton at Stanford decided to try doing neural networky type things on large amounts of data without any real reason to expect that the results would be dramatically different than what would happen with small amounts of data, but they were different, and here we are. We've got to get the data. And at the moment, we are nowhere near having that data for mice.
And even with all of the years and years of studies in them.
That's right. I mean, at the end of the day, you've got to have the right tools. The reason why there are so few organisms, so few species that are used in biology research is because a lot of things that you need to do in order to do an experiment that's actually informative are highly species specific. You can't just copy what you did in another species. You've got to do a lot of grunt work to figure out how to do experiments that work, that are informative. And long and short of it is that in mammals right now, even in mice that have been used for 100 years in experiments, we still don't have anywhere near enough information, which is very troubling because a lot of the newcomers to the field, especially a lot of the wealthy newcomers to the field who are writing the big checks, are not realizing what I just said. They're looking at what AI is already achieving, things like AlphaFold, for example, and they are saying to themselves, well, AI is going to be the solution to getting us to longevity escape velocity. Let's put all my money into that. Which is short-sighted, shall we say. I was going to be ruder than that, but no, it's short-sighted. Because AI will not be able to do fuck all unless it has the data. We need to be gathering a lot more data in order to empower AI in the fullness of time. And I need to get that across to everybody who writes big checks.
Very interesting perspective. Yeah, being kind of immersed in the AI space and, kind of how you're alluding to, there's the Rejuve.AI doing the fly work, and then you have Rejuve.AI collecting the human data, from all the biohackers and people that are super into tracking all of this stuff all the time. And one of the ways that we're kind of incentivizing on that side is via some cryptocurrency tokens, RJV. And we did notice that at the last Longevity Summit Dublin, there was a session about Web3. And I also know that you have a little bit of history with some, funding in that realm. So I just wanted to ask you a general overview of that industry and how do you think it will impact longevity?
So yes, it's been very heartening how much the crypto community have embraced the rejuvenation field. Way back in, I'm going to say something like 2017, when crypto became mature enough to actually start running its own conferences, I started getting invited to speak at them, and I would always be the only non-crypto speaker, right? I would be the only person. I was just there because of the fan base. People just wanted to know about this thing. And, it's kind of not surprising because, I think about aging with the mindset of an engineer, and, crypto people are geeks, right? Plus, also, they are happy to think outside the box and do things that are not very orthodox. So that's useful for something like aging. And the final thing that really matters is, of course, they're young. Most people in the crypto space are in the younger generation, and they have not been ground down by failure over decades of frustration. So, they're still capable of aiming high, which is definitely something that one needs to be in order to work on something so difficult as aging. So I've had a great deal of support from the crypto community over the years, and that does continue. But I will say that the crypto community are conversely guilty of what I was saying in my previous answer of kind of being overly breathless about the potential for AI to essentially sidestep all this boring wet stuff that we have to do in labs.
I feel like crypto and longevity are very similar fields in terms of there's a lot of unknown, there's a lot of exterior or outside skepticism about both because there's so much that is to be determined in both of those fields. So I feel like they go in hand together because there's just so much exploration that needs to be done in both of them. And a lot of times I think sometimes people give both of them a bad rap for being just a little more out there. But really, I think it's just a little people being scared or being like, we don't know what's going to happen with it. We don't know if we're going to live for forever. We don't know if digital currency is going to be the future and things like that. And so I think that there's so much more that has to come in the next couple of years that's going to be really tying those two fields together, hopefully.
Well, you're absolutely right. Yeah, I mean, certainly my perspective since way before crypto came along, like really the entire time that I've been working in this field, has been that people are terrified of getting their hopes up. And that is why they insist on indulging in these ridiculously irrational rationalizations of aging, arguments that have no logic whatsoever to say that, aging is some kind of blessing in disguise, or alternatively, that it's kind of woven into the fabric of the universe and there's nothing we're ever going to be able to do about it. It's so painful to have to answer these fucking same questions over and over again, which I spend my life doing, of course. And of course, I'm not the first person, as I've been mentioning earlier. Cynthia before me and Michael before him, or her. So yeah, it's painful, but I agree that yes, being willing to move beyond that, to transcend that, and to embrace the idea that technology can do things that most people think it can't, is something that my work and the work of the crypto world have very much in common.
Yeah, that's why, I was wanting to ask some things that are a bit less boring and, a bit more exciting than just, your run-of-the-mill things. Because I know I've seen you on like a ton of different podcasts and shows and things of this nature. And I guess like on the crypto thread, you went to the Vitalia pop-up city thing. I didn't make it, but I heard it's really amazing, and I'm going to check it out probably, in the not so distant future. But I mean, that's another example, right, of the convergence between, Web3 and longevity. It's like an interesting thing that's just emerging, right?
Well, absolutely. Yeah. I mean, Vitalia was a kind of an event. Well, it's kind of become a kind of event without end. But originally, it was just going to be a 2 month thing happening in a special economic zone in Honduras named Prospera. It's actually on an island called Roatan, which is off the coast of Honduras. And the reason why it's so special is because Roatan, well, Prospera specifically, has a very broad-based legal autonomy. They can make their own laws on most things. And in particular, they can make their own laws in relation to regulation of medicine. And they are using this fact very, very effectively. They have created a regulatory regime that is just as rigorous as the FDA, but very much more streamlined, very, very much more, such that things can get approved quickly. Now, of course, being approved in one place in Honduras is not the same as being approved in the US, but there is this thing called FOMO, that actually may make a huge difference in terms of the incentives for established jurisdictions to modernize their regulatory procedures. And that will happen if and when Prospera becomes a really conspicuous global hub for medical tourism. Medical tourism, of course, is restricted to people who have enough money to travel and also, to be honest, people who are willing to be early adopters. But you don't need all that many such people to create FOMO. So I have very high hopes for Prospera and for
Okay, so
Vitalia.
I mean, we've heard a lot about it. Do you recommend going? What was your experience like there?
Well, I went partly in order to, lend my support and prestige and all that, but also just to find out how well it was doing, what it was saying it was doing. And yes, I mean, everything I just said in terms of its prospects for becoming, as I say, the global hub of medical tourism arises from what I saw when I was there. They know their shit. They're doing things right. Um, so yes, I very much recommend going, at least for a few days, just in order to have that same experience, to see it, with one's own eyes. I will do my best to get back there every so often, perhaps for a week each year, something like that. And of course, some people are doing a lot more than that. They're creating companies there, they're relocating their companies there.
Yeah, I've been to Rotan. I have not
yeah,
been to Vitalia, but I've seen it a lot recently. But Rotan is beautiful. Beaches are nice and warm. It's like an ideal vacation place. So
Yeah, that was helpful in getting the place going. The fact that it's already a very established tourist destination because of the diving. It's got the second biggest barrier reef in the world after the Great Barrier Reef in Australia. And so, it's obviously Spanish is the first language, but there's a very high incidence of people who speak English, which helps. But also, it's very important to understand that Prospera is not just the whole of Roatan. It's 1 square mile or so of Roatan, and it's a gated community. It's very prosperous, and it's very well protected, very safe. I mean, Roatan in general is very safe compared to the mainland of Honduras. It's got less crime than, if I remember rightly, I saw the statistics, less crime than 45 of the 50 US states. So, and that's Roatan overall. As I say, Prosper itself
interesting.
is
Okay,
better than
well,
that.
you've convinced me to put it on my bucket list now. So I feel like that's
Right.
Yeah.
We're all gonna live
You
forever,
know how to use the word
right?
bucket list, right? Because bucket it's in the same way that when I give an award for having done a great deal in the field over a number of decades, which I give every year at the Dublin conference, I refuse to call it a lifetime achievement award because that implies that one has some idea when the person
all
is going
right.
to
I will not
die.
call it a bucket list. I will call it something I'm looking forward to doing in the future.
Yeah,
All right.
we'll come
Yeah,
up with something
figure that
there.
out later.
Yeah.
Right.
Aubrey, thank you so much for joining us today. Like I said, we could make this go on for a really long time, but unfortunately we have to wrap it up.
Thank you for having me.